Okay, so today in this video we're going to learn about whether root 2 is irrational or rational. In order to understand that whether root 2 is irrational or rational, we have to go through some of these concepts that I have right now with me. Alright, as you can see here, I've got a number line over here. As you can see that it is starting from, it is going towards minus infinity and from 0 to the plus infinity, and we are calling these numbers as integers. Alright, so whenever we consider this number line, so what do you think that we could have in between these two numbers? Maybe again the similar type of numbers, means if I take 0 and 1 and then I again divided this 0 and 1 into some proportions, right? So what I'm going to get again the same, if I divide this 0 and 1 into same proportion by using these same numbers, that does not make sense, right? So we should have something different than these numbers. Let's name these type of numbers integers for our ease. Now, for example, if I exchange this 0 and 1 here in this line, and now I see that here we have the starting point, here we have is 0, and the end point here we have is 1. Now we cannot have the same numbers here, as I already said. We should have something different than that. So what we can have, we can divide this line or make proportion. If in this line that is from 0 to 1, we can have some proportions. For example, as you can see, the 0 and 1, the middle part, that is the half of that is half plus half, that is making this full. So I am having this fraction number over here, that is 1 by 2, or I can say the proportion that is equal to 1 by 2. The proportion of 0 and 1 exactly in the middle is equal to 1 by 2. All right, so what if I do the same with the this 0 and 1 by 2? I'm gonna get again some number which is even smaller than 1 by 2, because it is going towards 0, and it is equal to 1 by 4. I can do the same to this 1 by 2, and the middle part, the middlemost part, is equal to 3 by 4, and it is greater than 1 by 2, and it is going towards 1. So on, we can do infinitely many times to that. For example, how we can get this middle term through mathematics. For example, now we can get the middle term by dividing the portion by 2, because we want that portion to be half, right? So we are dividing it by 2, or we can say that we can multiply this portion 0 and 1 plus 0 plus, for example, in this scenario we have 0 plus 1 by 2. So in this case we have 0 and 1 by 2, and when we add this up and divide this by 2, we are going to get 1 by 4. Or you can have it in another format, that is dividing this 0, multiplying this 0 plus 1 by 2 by half will give you the same number, that is 1 by 4. So by doing that, we can get infinitely many terms between 0 and 1. Alright, so what Pythagoreans think that we have all the numbers, that is we have all kind of numbers, we consider them as fractions or proportions, and they name these numbers rational numbers. So we have here rational numbers. As you can see, we get infinite number of terms between 0 and 1. You can do the same with 1 by 8 and 1 by 4, the middlemost term of this, and 1 by 4 and 3 by 8, the middlemost term of these two. And then we have another, and you can keep on going on and going on, going deeper into that precision. You're going to get infinite many terms between 0 and 1. So similarly it goes with every number, or in between every integer, so you're going to get infinite many terms. And they give the definition for that thing is, in order to remember it easily, they say that every number on a number line is in the form of p by q, means they are fractions or they are proportions. Give any if 0 get multiplied with any number, cannot give you that integer, right? So this condition will not satisfy. So in this case q should not be equal to 0, and p by p by 0 is not defined, so it is undefined. Now we have all the numbers on the number line is in the form of p by q. For example, we have 1 can be written as 1 by 1, and if we reduce it down, we're going to get 1, right? So we can do it similarly with 2, that is 2 is equal to 6 by 3, where 6 belongs to integer and 3 also belong to integer. And when we try to reduce it down, we're gonna get that is equal to 2. And we can do this similarly, to all the integers. 18 can be represented by 90 by 5. If we reduce down this 90 and 5, we're gonna get 18. So if you observe that whenever we are reducing down to the form where we cannot reduce even further, we are getting some fractions or proportions in this form. That is, we have, as you can see, we have 5 by 8 or 3 by 4. One is odd, one is even. Here one is odd, one is even. Here we have one is odd and another one is even. So all these numbers are present in the form of odd or even. Either they are odd or even or odd, you can say anything. So we have all the numbers or the rational number, when reduced down to some factor, reduced down to some fraction, we are getting numbers which are either the numerator belongs to numerator called as even, and the denominator called odd. Alright, so we have here every number on the fraction line, fractions on a number line is irreducible, means we cannot reduce it even further. We cannot reduce 3 by 4 or 1 by 2, 3 by 8 anytime here. So we cannot reduce these numbers here. So in this case we can rephrase this sentence and can say that 1 is the only factor of these numbers. As you can see, 1 can divide 1, 1 can divide 2, and you can do the same. You can say similarly to this or this as well, that is 1 can divide 5 and 1 can divide 8. So we can say that 1 is the only common factor left. So all the rational numbers that we have, as I said, that these q represent rational numbers. What the Pythagoreans say about that, the definition, that these rational numbers is always in the irreducible form, means they cannot be reduced further, and their common factor will be equal to 1. So this is pretty much here we have. So moving on to next concept, or going deeper into the concept that we have here. Right. So as you can see, these numbers right over here is considered to be fractions, and it is called as rational numbers because all the numerator and the denominator of all these numbers belong to integers, right? So they must be somewhere on the number line. All right, so what if we actually divide these two numbers right over here? Let's see what we can get. By dividing 3 by 8, we are getting 0.375. Another type of number, that is, we call it as decimal number, decimal expansion of fraction numbers. And we will try to find out what is the decimal expansion for 5 divided by 7. That is, we've got another type of decimal expansion, that is 73.142857 and 142857. This part right over here is getting repeated again and again here. We've got another concept over here, that is 3 by 10, that is equal to 0.3, which is terminating. And we have another example, that is 10 by 3, which is equal to 3.3333, and it is going infinitely many times. So pretty much we have, if we divide any fraction, if you take any rational number and try to convert them into decimal number, we are going to end up with these two types, that is terminating or repeating number, or terminating or repeating number, or just terminating number, terminating decimal number. Why we require decimal expansion? What is the purpose of decimal expansion? And what is the difference between decimal expansion and the fraction? Let's see what we can get. Okay, all right. So why do we require decimal expansion? Basically, we divide any fraction just to get a precision over that fraction. For example, 1 can be written as 0.9999, or here we have another example, that is 2 can be written as 1.9999. all right, or either 2 can be written as 2.000001. For precision, decimal expansion is required, and these numbers, as you can see, are going indefinitely, infinite times. They are getting repeated infinite times. So as to get the precision,